And now, from the implicit function theorem, we know that, I don't know whether I forgot to mention, the map phi is C1 here, okay? Phi is C1. Phi is C1. So how to compute the derivative of phi? This is also an important problem, okay? So we want to study how to compute the derivative of phi at a point x for x in O. How to do this? Now we consider this map, capital phi. Capital phi map x to fx phi x. Okay, so this map is a composition. So we map x to x phi x, and then fx phi x. That is our phi here, our capital phi here. So this is the composition of this map and this map. This map is precisely capital F. Of E1 and capital F. Therefore, by the chain law, before using the chain law, we also know that this is actually a constant map. It is constant because by the property of small phi, capital phi x, that is fx small phi x, which is always 0 for any x in O. Okay, so this is a constant map. Therefore, the derivative is 0. But what kind of 0? X is m-dimensional. X is m-dimensional. The value here is n-dimensional. So phi prime x is the 0. This is an n by m 0 matrix. You should know that this is a metric, not a number, because we are talking about vector valued functions. Okay, so on one hand, this capital phi is constant map. Therefore, the derivative is a 0 matrix. 0 metric. On the other hand, by the chain law, 0 is the derivative. Then this is by the chain law is the derivative of capital F and the derivative of g at x. The map we denote by g. So this map we denote by g. Gx is x phi x. Okay. So the capital F, the derivative of capital F in metric form can be written by dxf x phi x and dyf x phi x. And the derivative of g, because gx is x phi x, so it is easy to compute the derivative of g is the identity metric and then the derivative of phi here. Okay. Then making this metric multiplication. This is the capital F plus capital F x phi x phi prime x. Okay. So this is the computation. Now we want to compute the derivative of phi at the point x. We want to compute this guy. Okay, we want to compute this guy. But we have an equality involving the object we want to compute. But to solve this equality for the phi prime x, we need this metric. This is an n by n metric. We want this metric to be invertible. But this is the case because when x equal to a, for x equal to a, this metric is precisely the metric a phi x is b. This metric is invertible. This is the condition of our inverse function theorem. So at the point x equal to a, this metric is invertible. Therefore, near a, this matrix is also invertible. So we can multiply both sides of this equality, this metric equality, by the inverse of this metric to obtain we get 0 is dx f x phi x plus dy f x phi x and then phi prime x. This is the equality of our last line. So we have no space to write in this page. Therefore, we copy it to the next page. That is this equality. Now, as I mentioned, for x near a, this metric is invertible, right? Because it is invertible at the point A, then by continuity, it is also invertible near A. What's wrong? Invertible. Therefore, we multiply the inverse metric, we obtain phi prime x is minus dy capital F, then dx capital F. Here, phi is a map from O to omega. O is n-dimensional, omega is n-dimensional. So phi prime x should be n by m matrix. Okay? And also, our f, which with respect to x, is an n by m metric. And also, this is n by n. So this, the right-hand side, the two metrics on the right-hand side can be multiplied. And the result of their multiplication is an n by m matrix. So this matrix is the minus metric of our phi prime x. Okay. So this is the theoretical formula for the computation of the derivative of the implicitly defined function phi. Of course, it's a vector valued function. But now, this is not the practical method to compute the derivative of phi, because sorry, I forgot to write the inverse metric here. So I need to inverse. I forgot to write the inverse, because the to compute the inverse metric is very complicated, and also the metric multiplication is also complicated. So in practical application, because we have f x y is 0, here we regard y is a function of phi. In component, we have the component's form is f I x1 xn y1 yn is 0. Here y1 yn are function of x1 xn. Okay, so this is our phi, our implicitly given map phi maps x1 xn to y1 yn, and they are connected by this equality or equation for all I from 1 until n. Our capital F has n components, so we have this n equality. So we consider this yi, y1, y2, yn as a function of x. We take the derivative with respect to xk on both sides. So we get capital dxi dxk plus by the chain law, dxi dyj dxk j from 1 to n. The right hand side, remember that y1, yn are function of x1, xm. Then taking the derivative with respect to xk on the left hand side and applying the chain law, the derivative of the left hand side with respect to xk is this expression. Of course, because this is actually 0, so the derivative is also 0. So we have this correspondingly we have this inequality. Okay, we have this inequality. Now, from this, we consider this as since the metric, this metric I and j from 1 to n is immutable. We consider this as a system of linear. We consider this as a system of linear equations which are known dyk dx dyj dxk. We consider this as the unknown quantity. We can solve using the Cramer law. We can solve for the partial derivative of yj with respect to xk by the Cramer law. This is linear algebra. Okay. So this is a more practical method to compute the derivative of phi point x. Remember, our yi equal to yi x1 xm is the coordinate expression of phi. Therefore, the derivative of phi at x, phi point x actually is the metric dyj dxk. Okay, so having computing all the dyj dxk using this method by Cramer law, we can eventually write down the derivative metric of our implicitly obtained function phi. Okay.